we are talking about. So silicon has what we call as diamond lattice. Diamond lattice, it's it can be thought of as interpenetrating FCC lattice. We say interpenetrating. We There's a way how we look at it. So, but if we know the basic structure, we can find out exactly how many atoms are there in a unit cell. How many atoms are there in a given plane, right? We talk about planes also, what we call Miller indices, a set of three numbers that helps us identify a plane in a lattice. Because knowing the plane helps us know exactly how many atoms would be there in that plane, right? So this was an exercise we did where we were given uh, silicon information, right? Lattice constant 5.43 angstroms, which is always going to be the same for silicon, right? Wherever you encounter any problem with silicon, 5.43 angstrom is what you use. And we played with the numbers and we looked at, okay, how many atoms were there in a plane. And this was 100 plane we are looking at. We calculated the area of the plane and then we just divided that to get the density. And we use density instead of using the actual numbers of how many would be there. So density helps us make it more uniform across different things. And then we calculated the volume, right? So the idea is that we could use this information to now exactly know how many atoms are there. And especially when we are talking about one element like silicon, this is straightforward. But that's not always the case. Many times we may have different number of different elements and they go in combination. So we have silicon from group 4. So group 4 means there will be 4 uh, electrons in the outermost shell, and then there will be 4 valence positions, 4 empty positions. Now if you go to group 5, that means there are 5 electrons and 3 valence positions. If you go to group 3, then what we are essentially saying is that there are 3 electrons and 5 valence locations where potentially electrons can come in. So hence when we talk about compound semiconductor, we always talk about group 3 and group 5. So group and group 5, they come together and we get a compound. Or we talk about group 2 and group 6. Again, the same thing. In group 6, there are uh, 6 electrons in the outermost shell and 2 empty locations. At group 2, there are 2 electrons and 6. So once they come together, they would form 4 bonds. So every atom makes 4 bonds with 4 other, which we see here in the diamond lattice. So we'll come to what's written here at in the bullet point, but I want you to focus on this picture. This is the diamond structure, and the simple way of identifying diamond is that this has this is an basically an FCC lattice, but this has extra atom placed at A by 4 plus B5 by 4 plus C by 4 from each of the FCC atoms. So hence, we see the location for these atoms in the air. Let me just identify which are those extra atoms which are here. So this is that guy, this is that guy, this is that guy, and this is the bad guy, right? So understand this with me that all other atoms like this one, let me change color, they don't belong, they belong to locations of FCC, right? And talk to me if you don't agree with me, because knowing this is important. So this belongs to the corner of FCC. This belongs to the face of FCC. This belongs to that face of FCC on the other side. So this belongs to a face of FCC, this belongs. So you all agree with me here that we have an FCC and then we have four atoms which I've highlighted with red, which are a quarter of vector away from in all three directions, A by 4 plus B by 4 plus C by 4. You are with me on this? We have to agree on this before we get to the next concept. We have to understand this. And if you don't understand, raise your hand. I want to see that now so we can uh, break it down and see what other things are involved here. All right, a few of you still don't have your video on. It does not help me if I cannot see you, if I cannot get visual cues that we all are uh, learning something. All right, so I could mark all those which belong to a regular FCC, but since we all agree, we'll just move on to the next idea. So these three are what you would call as the extra four atoms that are part of. So this is to the back, this. So the red ones are those four which define a diamond lattice. Okay. Now, once that's out of the way, what's important here now is to, if we look at this structure from, say, from the top, what we see is we see that there are kind of two interpenetrating FCC sublattices. I know we cannot see this here in 3D, but if you look at this from the top, you would realize that there are two FCCs which are kind of digitated or interpenetrating each other. Now, basically, then there will be two FCCs which can be shown to be part of each other. But that's something which would help us when we talk about doing a little bit more detailed analysis of crystal structures, but we will not do that. So for us, we will stick to basic diamond structure and another special type of diamond structure. So now diamond structure is when all the atoms belong to the same element. But if you have two elements, and what are those two groups that come together? Can somebody tell me? I just told you what are two groups that normally come together? This is where you can push your spacebar and you can speak and I'll be able to hear you.
3 and 5.
3 and 5. All right, that's one type. And another type?
4 and 6.
2 and 6. 2 and 6 come together. Now, when 3 and 5 come together, what happens is instead of all belonging to one type in this structure, then there will be alternates that will be there. So if I have to color now, if this would be one type, maybe group 3, all others that it's connected to will be group 5. So then all others that it's connected to will be group 5. Sorry, did I? Yeah, so this guy has to maybe made up to clear. Let me clear everything and start fresh. So now if I were to take one atom, any for that matter, say I pick this one. So this will be now connected with, if this was group 3, all others that it will be connected will be group 5. So, and it connects with 4 of them, right? So now if I pick any of the red ones, I will see that each of those red ones, let's pick this one, is now connected to group. So here would be something here at the bottom, and this is not showing because that goes out of that unit cell. And there's one at the back also. So that red one will be connected to 4 green ones, right? Alternate sites. So let me pick another one, another green here. For example, I pick this green. So if I were to see what are all four atoms it's connected to, red we already see on this side. This will be a red, this will be a red, and it's going back to this would be a red. So now, and uh, what do we call that kind of material when you mix 3 and 5? It's an alloy, right? They don't chemically react, but they bind to each other and they are part of a structure. Now, when I say chemically react, they don't result into a chemical reaction where you get another products. And the difference is because each atom is maintaining what it is. And if I were to look at a simple example, 3,4 compounds, there is gallium arsenide, for example. So that's gallium is from 3, arsenide is from 5. So gallium stays, gallium arsenide stays arsenide, and they're connected and they're sharing their atoms with covalent bonds. All right. So when you do this, we call this structure as zinc blende crystal. So it is basically diamond, but because diamond is meant for only for one type, when you have two types, then we call it zinc blende. All right, where are we going with this thing? Because doing this makes a semiconductor change its properties. We can change its electronic properties, optical properties. We can uh, basically have very different conductivity when we do this. Now, how do we see group 3 and group 5? So essentially, we would create something which can have more than one elements from one group. Okay, I'm throwing another wrench in this discussion. So aluminum is group 3. Both gallium and arsenide are group from group 5. So what we can do is basically, because what matters is what is how many electronic states are available in their outermost shell. That's what defines group 3, group 4, group 5, right? So everything that belongs to group 3, we have 3 electrons in the outermost shell and then 5 empty spaces. Whatever comes from group 5, we have 5 electrons and 3 empty spaces. So you can take 2 from group 5 and mix with one group 3. So for the atom from group 3, it doesn't matter what type is coming from group 5 as long as they are compatible, right? All it has to do is share its electron and complete 4 electrons in the outermost shell, complete 8 of them, right? It will bring some. So we have a picnic, you bring sandwiches, I bring drinks. I don't care if 2 of you bring X number of sandwiches or 5 of you bring X number. All I need is X sandwiches, right? And I will bring uh, Y number of bottles. It shouldn't matter for you how many people pitch in to bring Y number of bottles, right? Think of it like a picnic. So you're bringing a number of atoms, number of material from group 5, number of material from group 3, we bring them together and they would form a crystalline structure. So here's an example of aluminum gallium arsenide. So if I stop here and ask a question, why are we doing this? Why do we mix different materials? Why do we mix different materials?
So we can change the properties to conduct
Electronic properties. So we
electron.
can adjust electronic properties, optical properties. All right, so if I tell you that, but just by adding maybe a quantum amount, I don't say that, shouldn't say, like nanogram of a material can change the wavelength of that material dramatically. And wavelength means maybe it's a it's a photodiode. If it was giving, say, red light, by adding small amount of other thing, it can start giving you maybe green light or blue light, right? So we can change their optical property. In a similar way, by adding small amount of that material, we can dramatically change the conductivity. So hence we play with these things. There are a couple of important things that you would need to know. It always makes a good quiz question or exam question, and which is that how do we know how much of what is being involved in there? We normally write it as a subscript of the amount that is being used. For example, I've written here, I just wrote aluminum gallium arsenide, right? And I said we can vary the composition of this alloy by changing the fraction of aluminum or gallium atoms. So, oh sorry, these two come from 3 and this one comes from 5. So what we can do is we can change aluminum, gallium, because arsenic, group 3 and group 4 have to be equal number, equal amount. But within 3, I can change amounts. And this change or this relative fraction is written as a subscript, X, or and if one is written as X, think about it, we have to make 100%. We can write the percentage, you can write one of them as maybe 30, then you don't have to write the other. We can just write 1 minus 30 or 100 minus 30, it will give you the other fraction. So hence we write it in terms of just write one fraction and we write the other in terms of how much is left behind out of 100. So one is basically depicting, we take one as a unity and we say, okay, with respect to unity, how much of the other one is there? Because this translates into percentage. So that example with the subscript, when you write the real material thing, we automatically translate it into percentage. So this is called a ternary compound. So if you have only 2 of them, for example, gallium arsenide, you would call it a binary compound, 2 of those. If you have 3, you'll call it ternary alloy. If you have 4, what would you call it? Quaternary. So it's just a way of knowing how many elements are being involved into creating that material. And then if you write, for example, this thing, that will tell me right away that there is 30% aluminum, 70% gallium, and they both are from group 3, and then equal amount of these two combined is group 5, which is arsenic. We do this because that changes the properties of the material. And as a designer, if you are, say you're working on a rocket, you're working on a satellite that you have to throw up, you have to change the crystal to have different frequency, you will know what kind of material you need for that, whatever frequency you are using. Now this gives us control over having like unlimited range of frequencies that we can generate from these materials, from semiconductor materials. We'll look at that later on. So here I'm just saying that how do we understand the fractions? We write it from 0 to 1. And now when you have quaternary compound, you would use X for group 3, and then you will use a subscript Y for group 5 elements. We'll come to that. Let me just jump to this picture here. I brought this picture to show that how would the fraction result into changing lattice constant, right? What was lattice constant for silicon?
5.3.
5 point, yeah, almost close. So 5.43 angstroms. Remember this? Now, I said that it is a constant, right? For silicon, that's a constant, yeah. Now, by changing lattice constant, what can happen? There are two new things I'm introducing here today. By changing lattice constant, okay, we cannot change a lattice constant for an element. We cannot change lattice constant for a material in a very specific composition. For example, here it says x is equal to 0.2. Now, this is a quaternary compound here. We are dealing with indium gallium arsenide phosphide or aluminum and aluminum gallium arsenide antimony. What's happening here is we are changing relative concentration of these two between group 3 and these two between group 5, which is this light blue curve here. And we are changing relative concentration of group 3 and group 4 here, which is shown in this black curve. Just stay with me and you'll understand what's going on, hopefully. But we'll come back to this later on. What's happening is we have defined a system of materials where we say, okay, we can mix 2 of group 3, 2 of group 5, and we can create an alloy. And we can change relative proportion of group 3, relative proportion of group Y. When you do that, your lattice constant is changing. So all the way from here, if I were to put a line there, all the way from here, the lattice constant is something 5.46 here. And this is gallium phosphide, which means no indium, no phosphide. And if I start adding other material, for example, I start removing phosphide and start adding arsenic, somewhere here, the whole phosphide is gone, only arsenic remains in that material. So I get indium gallium, I just get gallium arsenide. I haven't introduced indium yet. What's the lattice constant here? Probably 5 point. Can you help me? What would be this number here?
Like 5.65.
5.65. All right. So now think about it. The lattice, how close the atoms were to each other, have gone apart, gone away from each other, right? Lattice constant has increased. Now, if you think about that example where we calculated the number of atoms in a unit cell of silicon, we would have fewer and fewer cells. Let me go back and show you. Let's go back to this example. So if you were to do this, the unit cell size has increased because the lattice constant has increased, right? So now density has gone down, which means that there will be fewer atoms available in that same amount of material, which would probably mean less conductivity. Are you with me on this thought process?
Yes.
All right. So
as the lattice increases, the density decreases, right?
of course, think about it. If you have how many in this volume, there were 8 atoms, right? We are dealing with the same structure, 8 atoms in small box. Now your box is bigger and you have still what, 8 atoms. If you have to find number of atoms divided by volume, volume goes up, density goes. If the volume goes up, what happens to the density?
Goes down because the mass is
It
the same.
should go down, right? So what is this? Number of atoms per So basically density is what?
Mass per
Number
unit volume.
divided by volume. The number is still the same. It's the same structure, diamond structure, or what you call zinc blende structure, because there are two atoms, two different types of atoms. The number of atoms are still the same, but what happened? Let me go back to that example. Your lattice constant has gone up, which means the volume has gone up. The density has come down. All right, so that's one implication. Now, what is shown here on y-axis is something which defines solid state devices, which defines band gap. So we have a thing called band gap. We haven't talked about it yet, but I just want you to trust on me that the band gap is basically the energy difference between valence band at bottom and conduction band at the top. Maybe you remember high school physics where they talked about valence band and conduction band and atoms jumping and going to the conduction band to become available. So those bands are basically nothing but energy levels. So if band gap goes higher, you need more energy for atom to become available. You need more energy for that electron to become available for conduction. If the band gap becomes less, you need less energy to make that electron active for your conductivity. So what's happening here is not just lattice constant is changing. I'll go back to this simple example again before we get into other things. So going from here to here, there is a change in the energy of what you call band gap. And if I were to measure, this would be probably 1.4, somewhere around 1.4, and this is 2.25. So there is a 50% increase, I would say, in the band gap. So you need to crank up more voltage maybe to your solid state device to make it active. I will not hammer down this concept today too much, but this will come later on, much more detail. Now, two messages so far that if we have instead of just using silicon, if we use a number of different materials to create what you call compound semiconductors, we can adjust the relative concentration of compound materials that go into that to change lattice constant and to change the band gap. Hence, we can adjust the electronic properties. And compound semiconductors are not just binary, they can be ternary and they can be quaternary. And how do they come together? They come together, many of those come together in this structure, what we call as zinc blende, which is a modified, which is nothing but diamond structure, but the difference is diamond is supposed to be for one element, and if you have compound, then it's supposed to be two elements or more, right? So let me come through these slides again. I don't want to hammer too much material because I know all these things are new for you. You have never seen those before. So trust me, if I'm going slow, but there's a lot of information coming in. So again, if I recap, we write these things like this, where there are group 3 elements, group 5 elements, or group 2 and group 6 elements. So that's the combination they work. And this small subscript tells us what is the relative concentration of one group elements. Here I just showed you 3 compounds, but they can be 4 compounds also. For example, we can mix 4 elements, 2 from group 3, 2 for group 5. It can be 2 for group 2 and 2 for group 6 also, right? But let's look at a simple example. So what we have done here, all right, questions, and there's too much information, questions. All right, so what we can write is, we can take 2 group 3 and 2 group 5, and that becomes a quaternary semiconductor. Between these two, on group 3, we can rotate, we can change their relative concentration, right? So, for example, here I can write indium with X. For example, I say 0.53, which means 53% would be indium, and 100 minus 53, what remains? 47% would be gallium, right? I can also define relative concentration of group 5. In that case, we use Y, we don't use X, because X is already being used to define how much would be indium. So in that case, again, 1 minus Y is nothing but just telling us, if you have used some amount of this, remaining amount is the other type, right? So we can dial up between group 3, 2 of them. We can dial up between group 5, 2 of them. We use X to show how much of what is being used for group 3. We use Y to define how much is being used for group 5. All right. Now, why we do that? That would change the lattice constant, and hence it would change the band gap of the material. So this is essentially what I showed you on the slide. This is all the same information just given here. That we can change the lattice constant by changing the group 3 elemental composition in a ternary alloy. But if it is a quaternary alloy, then it is not a linear change. Then the change, we calculate the change. So we know the change, and that's what we plot like it is shown on this slide. Now I'm ready to dig deeper on this, in this guy, a little bit more. All right, so what's happening in this figure is we are changing group 3 and group 4, sorry, group 3 and group 5, both relative between themselves. If I were to identify group 3 with red and group 5 with green, green is not visible. Let me make it blue. Right, so if you see here, indium is 0, arsenic is 0. No amount is there, right? Do you agree with me? So you have to change colors. So these are, if I were to go by blue for these guys. So what's the situation here? Arsenic is 0 here at this point. So what they're doing here is they are not adding any indium, but they are going from here to here, where gradually increasing arsenic and gradually reducing this P phosphate in this process. You see that there's no indium, but arsenic has become highest and P has become 0. Right? Now, from this point to this point, If I follow the chart, now they are keeping group 5 arsenic as it is, but they are now changing the group 3 element, which were IN and GA, indium and gallium. So at this point, indium is 0, gallium is 100%. Are you following me? But when they get there, the gallium is 0 now, and indium is 100%. And during this process, the material is going through changes in lattice constant and the band gap both, right? Now, this process is doing another thing. The wavelength, which relates to light, right? Light coming out. The wavelength is changing. You guys remember what are two extremes of wavelengths? If you have wavelength spectrum, what are the two extremes of that? Light spectrum. If you put light spectrum, what are two extremes? Ultraviolet and infrared. Remember that? What does infrared mean?
Oh, red before red.
Below the red.
Which is the frequencies below red. And what is ultraviolet?
Frequencies above violet.
Above the color violet. And so what happens across the whole spectrum? When the frequency changes, the color changes, right? That's exactly what we would achieve if these were optical devices, that we, by changing the relative fraction, we are changing the light they would emit or the light they would absorb. So we would be making photodetectors for our choice or photoemitters of our choice. That's exactly how your remote controls work, because they would have changed the frequency. Not all of them are visible, right? So infrared and ultraviolet is a very small part of the spectrum which we can see, but the spectrum is immense. We can achieve all those wavelengths by just changing relative fractions of the material. Let me clean this screen so we can just visualize and see what's happening here. So I stayed only with indium gallium arsenide here when we were talking, right? So I stick to only this thing. When we were talking this side, now you all have the book with you, right? I want you to do this exercise, all of you. Have it open, or you can look at it, because this is kind of, I'm asking you small questions. So if I were to design a photodetector for 1.24 micrometer wavelength, what should be my combination of materials? How would we do that? So I say, this is the number I called out, 1.24. Then I would put a line across, and I will start marking, okay, this is the combination. This is another combination for other materials. This is a combination. So you have to come back and ask me, okay, what are the materials that you have available? Do you have gallium arsenide and indium, gallium, indium, and arsenide? Then if I say that's what I have to do, then you will follow this one track and give me the exact relative concentration. So this would be probably from 0.4 to 0. Will be slightly less than 0.3. Your X will be slightly less than 0.3. So you'll plug in your X here, and you will tell me this is the material combination for your wavelengths that you need. Right? Are you following me on this? If I say I need a material that can give me 0.827 micrometer wavelengths, so then you'll pull this chart out and you will look at this guy and you draw a line and you say, okay, there are 4 possible combinations. What materials do you have for your fabrication today? I say, okay, I have aluminum, gallium, antimony. So you will say, okay, you will have to figure out what is the relative concentration between aluminum and gallium. And you say, okay, this is create, order this material in this relative composition. That would be the material for that application, 0.827 micrometer. Right? So band gap has a direct relationship to the wavelength. So that's another thing which we see. These two things are related. We'll look at their relationship later on. And they all depend on what is the X subscript X or subscript Y for different combinations. With me? All right, questions. Because these are the basic fundamentals of devices, device materials. We will build up on this information later on as well. Where we have to know few things, that we use alloys in different combinations and we know precisely how much of what is being used, and most of the materials would fall into the diamond structure or its variation, what we call a zinc blend structure, and their arrangement in the plane, the number of atoms that are there, they all will define their mechanical, metallurgical, chemical, electronic, optical properties. I added few more today on top of electronic and optical, which are our interest, but their mechanical, metallurgical, and chemical properties are also important because somebody has to fabricate these materials. Somebody has to make these devices in the clean room. So we need to know how are their reactions going to work out. Right? So I think let's stop here. This will finish the module where I wanted to talk about planes, unit cells, and the basic structure of semiconductor materials. I'll have the soft chalk posted, and we'll take it from there. Questions?
No, sir.
All right, very good. I'll let you guys go.
Thank you, sir.
Sure.
See you next
Thank you.
week. Bye-bye.
Have a good day.
Page is that diagram on in the book? Do you know?